Hello, my name is Louis Shower, and today I'll be talking about my Physics 2211 Lab 3 about black holes and orbits. First, like to go over some models and principles. For this project, we'll be examining orbit, so a star in free orbit around a larger black hole. This will look at Newton's first and second laws, which is the momentum principle, um, and then perpendicular and parallel forces, because we're talking about circular motion. And for this lab, I will be using GlowScript, Web v Python. And we're going to use these tools to create accurate digital model of a star orbiting a black hole. These are my results. This is the email that I inputted for my seed. That is supposed to be the mass that I got out. So if that looks familiar to you, then that's good, and if it doesn't, then don't even worry about it. I'll try to play this video. I don't know how long the video is. And then here's an image from the end of my lab, as well as a little picture of a black hole. I'd like to talk about some physics equations and ideas also. Here's the momentum principle here. F net equals change in momentum over change in time. And then we also have the gravitational force equation, which, as you can see, we will use to model the pull of a black hole on a star. And as you can see by the arrows, because the star has less mass than the black hole, it will be moved less by the same amount of gravitational pull. This may be from my last lab, but I think I've covered everything that I need to talk to. Obviously, there's no drag in space, and we're not really talking about the. Well, actually, that's true. We're not talking about the z direction, so we're assuming that there's no motion in the z direction. And here, that f of g is not what we're using, but I can just say that that's to contrast with that force of gravity equation. So that's not what we're using today. Calculations and preparation. So our system is a black hole and a star. The seed of the model is randomized using my inputted email. There's my email. If you have any concerns about my presentation, you can email me. I did this work to the right to solve for the mass of the black hole using the gravitation equation. The other variables are the constant g, gravitation constant g, very small number, F net, mass of the star, and position. And I assume the black hole that have to be at the axis, because I didn't really, so 0, 0, 0. And then I went through the code, solving for all the different variables required. Here are some pictures of my code if you want to take a look at it, see what I did, see what was going through my mind. And then that work on the right is actually not right. That's where I did the work originally, and I'm pretty sure it's wrong. So that's how I'm growing as a physics student. The work on the last slide should be right, and there's a picture as you can do. Here are my comparisons, analysis, and limitations. So the mass that I got was 7.452 times 10 to the 22 kilograms. According to the reputable physics website Vedantu, generally a typical black hole weighs between 3 and 10 solar masses, and one solar mass is about 2 times 10 to the 30th kilograms. So that might not be right. But that means that my calculations were not exactly on par with the mass of a real black hole. Reasons for the error might be that my model may be more effective with smaller numbers, or this might be an exceptionally small black hole, or I did the math/physics wrong. In which case, when you're thinking about grading, I made so much progress for my first attempt, where I got 3 times 10 to the negative 22 kilograms, and I'm growing as a physics student. Also, if I get your slideshow, I pinky promise that I will give you a 100. So just think about that. Here are some result photos. Again, this is a picture of my model at the end of its running. There's the mass that I got from my work. And lastly, we have some extension questions. For the first one, because of the momentum principle, I thought that they were equivalent, but I guess not. I guess because the momentum is m times v, and the mass is constant the entire time, we don't have to worry about it. But at the same time, velocity equals force divided by mass. That's also in Newton's second law. And the mass is constant here, so I'm not really sure what the difference is. But if you figure it out, feel free to email me. And then for the second one, we would also need to create models in GlowScript using the planets and moons, although by far the black hole will be the dominant force because its mass is magnitudes larger than any of the other objects. So if you made it this far, thank you.